universe has always told us stories through light. But light only reveals part of the truth. What if the rest is hidden in the shadows? What if the most important parts are the ones we can't see? We look into space and see galaxies burning across billions of light years. We see stars being born, planets spinning, nebulae glowing. Yet all of it, everything we've ever observed, makes up less than 5% of the universe. The rest is missing, not in theory, in fact, measured, confirmed, real, but invisible. There is something happening in the center of our galaxy. A silent signal. A specific burst of energy repeating over and over. Not from a star. Not from a planet. But from annihilation itself. It is the death cry of matter colliding with antimatter. A reaction so perfect, it leaves nothing behind but a gamma ray. And we are detecting them in massive numbers. These are not accidents. They form vast clouds, antimatter clouds, floating silently through the galactic core, invisible to telescopes, undetectable until they destroy something. Physics tells us they shouldn't exist. The Big Bang should have wiped them out. And yet, here they are, waiting. At the same time, something else lurks in the dark. Something that wears the face of a black hole, but isn't one. It bends space. It traps light. It pulls stars into its grip. But inside, it's not a singularity. It's not a void. It's a shell, a structure, a deception. These are gravastars. Objects that rise to form instead of black holes. They have no event horizon, no infinite collapse, no information loss. Just a dense shell, and inside it, nothing but exotic vacuum energy. A perfect mask. From the outside, they are identical to black holes. We could be looking at one right now and never know the difference. Two cosmic anomalies. One real, one theoretical. One destroys silently. The other hides in plain sight. They appear unrelated. Separate mysteries floating through space. But maybe they aren't. Maybe they are two sides of a deeper truth. Maybe what we see is only the cover of a book we were never meant to open. And when we finally understand what they are, we might wish we never did. This is the hidden universe. The story of our existence begins with one of the most profound mysteries in modern physics. According to our current understanding of the universe, you should not exist. Neither should Earth, the Sun, or any of the billions of galaxies we observe across the cosmos. The very fact that we are here to contemplate our existence represents a fundamental puzzle that has challenged scientists for decades. To understand this cosmic riddle, we must journey back to the very beginning of time itself, to the moment when the universe exploded into existence 13.8 billion years ago in the event we call the Big Bang. In the first fraction of a second after the Big Bang, the universe was a seething cauldron of pure energy. As temperatures began to drop from the incomprehensible heat of creation, this energy began to condense into the first particles of matter. But here's where our story takes a puzzling turn. The fundamental laws of physics tell us that for every particle of matter created, an equal amount of antimatter should have been produced as well. This isn't just theoretical speculation, it's a direct consequence of one of the most important principles in physics, known as charge parity symmetry. When energy converts to matter, it must do so in a way that preserves certain fundamental properties of the universe. For every electron that materializes from pure energy, a positron, its antimatter counterpart, should appear alongside it. For every proton, an antiproton. For every neutron, an antineutron. The implications of this symmetry are staggering. If the Big Bang had indeed produced equal amounts of matter and antimatter, the universe would have lasted only a brief moment before destroying itself completely. Matter and antimatter are perfect opposites. When they encounter each other, they annihilate instantly, converting back into pure energy with perfect efficiency. No atoms could have formed, no stars could have ignited, no planets could have coalesced from cosmic dust. Yet here we stand, 13.8 billion years later, in a universe dominated by matter. The stars that light our skies are made of matter. The planets that orbit them are composed of matter. Our bodies, our thoughts, our very existence, all products of a universe that chose matter over antimatter for reasons we don't fully understand. This cosmic preference for matter over antimatter is known as baryonic asymmetry, and it represents one of the greatest unsolved problems in physics. Calculations suggest that for every billion particles of antimatter produced in the early universe, there were approximately 1,000,000,001 particles of matter. This tiny imbalance, just one extra matter particle for every billion antimatter particles, is the razor-thin margin that allowed our universe to exist. When the vast majority of matter and antimatter annihilated each other in the universe's first moments, that minuscule excess of matter particles survived to become everything we see today. Every atom in your body, every star in the night sky, every galaxy spanning millions of light years, all of it represents the leftover remnants of this cosmic imbalance. But what caused this asymmetry? Soviet physicist Andrei Sakharov proposed 3 conditions that would need to be met for such an imbalance to occur. First, there must be processes that can change the number of matter particles in the universe. Second, both charge symmetry and charge parity symmetry must be violated under certain conditions. Third, these processes must have occurred when the universe was not in thermal equilibrium, during the rapid expansion and cooling that followed the Big Bang. While physicists have found evidence for some of these conditions, the observed violations are far too small to account for the massive matter-antimatter asymmetry we observe. The Standard Model of Particle Physics, our best current theory describing the fundamental forces and particles, can only explain a tiny fraction of the imbalance that actually exists. This leaves us with a profound question: what mechanism could have produced such a dramatic preference for matter over antimatter? Various theories have been proposed, from the existence of exotic particles that decay asymmetrically to complex interactions during cosmic inflation. Some scientists have suggested that antimatter might not be as rare as we think. Perhaps it has somehow been segregated into distant regions of the universe where we haven't detected it yet. The mystery deepens when we consider that antimatter, though rare, still exists in our universe today. Cosmic ray interactions in our atmosphere produce small amounts of antimatter particles every day. Certain types of radioactive decay create positrons. Even banana peels emit tiny quantities of antimatter as they decompose. More intriguingly, space-based detectors have discovered significant concentrations of antimatter in various regions of our galaxy. These observations suggest that whatever process created the original matter-antimatter asymmetry might still be operating today, continuing to shape the fundamental composition of our universe in ways we're only beginning to understand. Deep within the heart of our galaxy, something extraordinary is happening. Hidden among the billions of stars that make up the Milky Way's central bulge, vast clouds of antimatter are silently drifting through space, invisible to our telescopes yet announcing their presence through the most violent process known to physics: complete annihilation. These antimatter clouds remained completely unknown to science until the late 20th century, when our instruments finally became sensitive enough to detect their signature. The story of their discovery begins with a single, peculiar energy signature that puzzled astronomers for decades and ultimately revealed one of the most significant mysteries in modern astrophysics. High-energy gamma-ray detectors began picking up a strange signal from the direction of the galactic center. Unlike the continuous spectrum of energies typically observed from cosmic sources, this signal appeared at a very specific energy level, 511 kilo-electron volts. This precise energy signature immediately caught the attention of physicists, because it corresponds exactly to the energy released when an electron and its antimatter counterpart, a positron, annihilate each other. When matter and antimatter particles collide, they undergo complete annihilation, converting their entire mass into pure energy according to Einstein's famous equation E. For electron-positron annihilation, this process produces two gamma-ray photons, each carrying exactly 511 keV of energy, the rest mass energy of an electron. The detection of this specific gamma-ray line from space could mean only one thing: somewhere in the galaxy, electrons and positrons were meeting and destroying each other on a massive scale. The implications of this discovery were staggering. The intensity of the 511 keV line suggested that enormous quantities of antimatter were being annihilated near the galactic center every second. Calculations indicated that the equivalent of several Earth masses worth of antimatter must be destroyed each year to produce the observed gamma-ray emission. This represented the largest concentration of antimatter ever detected in the universe. For decades, the 511 keV line remained one of astronomy's most tantalizing mysteries. The limited sensitivity and resolution of early gamma-ray detectors provided only crude measurements, leaving scientists to speculate about the true nature and extent of the galactic antimatter phenomenon. It wasn't until the launch of more sophisticated space-based observatories that the full scope of this cosmic puzzle began to emerge. The European Space Agency's Integral Observatory, launched in 2002, revolutionized our understanding of the galactic antimatter distribution. Integral's advanced gamma-ray spectrometer provided unprecedented sensitivity to the 511 keV line, allowing astronomers to map the antimatter annihilation across the galaxy with remarkable precision. What they discovered defied all expectations. The antimatter signal was not confined to a small region around the galactic center, as many had assumed. Instead, Integral revealed an enormous, roughly spherical cloud of antimatter extending thousands of light-years from the galactic nucleus. This antimatter halo encompassed a significant portion of the galaxy's central bulge, with the highest concentrations occurring within about 3,000 light-years of the galactic center. Even more puzzling was the discovery that the antimatter distribution did not follow the same pattern as the visible matter in the galaxy. While stars and gas are concentrated in the galactic disk, the antimatter appeared to be distributed more spherically, suggesting that whatever process was creating these positrons was fundamentally different from the mechanisms that govern normal stellar activity. The observations from Integral and Fermi painted a picture of truly cosmic proportions.
Antimatter annihilation in our galaxy requires the production of around 10 to the power 43 positrons every second.
This leads us to one of the most perplexing aspects of the galactic antimatter mystery. We can detect the antimatter only at the moment of its destruction. The positrons themselves are completely invisible to our instruments until they encounter electrons and annihilate, producing the telltale 511 keV gamma rays. This means that vast clouds of antimatter could be drifting through space around us, completely undetectable until they interact with ordinary matter. The invisibility of these antimatter clouds presents both a scientific challenge and a potential cosmic hazard. Unlike ordinary matter, which can be detected through various forms of electromagnetic radiation, antimatter particles moving through the near vacuum of space produce no observable signature. They exist in a state of perfect stealth, revealing themselves only through their ultimate act of self-destruction. Several hypotheses have been proposed to explain the origin of these mysterious antimatter clouds. One leading theory suggests that the positrons are produced by the decay of dark matter particles. Dark matter, which makes up approximately 85% of all matter in the universe, remains largely mysterious, but some theoretical models predict that certain types of dark matter particles would decay into electron-positron pairs. The spherical distribution of the antimatter signal matches what would be expected from dark matter decay, making this one of the most compelling explanations. Another possibility involves microquasars, stellar mass black holes that are actively feeding on material from a companion star. As matter spirals into these black holes, it forms an accretion disk that can reach temperatures of billions of degrees. Under these extreme conditions, the intense radiation and magnetic fields could accelerate particles to such high energies that they produce electron-positron pairs through various nuclear processes. Pulsars, the rapidly rotating neutron stars that emit beams of radiation, represent another potential source of galactic antimatter. The powerful magnetic fields around pulsars can accelerate particles to enormous energies, potentially creating cascades of secondary particles that include positrons. With thousands of pulsars scattered throughout the galaxy, their collective contribution to the antimatter population could be substantial. More exotic explanations have also been proposed, including the possibility that primordial black holes left over from the Big Bang might be evaporating through Hawking radiation, producing antimatter particles in the process. Some scientists have even suggested that the antimatter clouds might be evidence of ongoing matter-antimatter asymmetry processes, indicating that the universe is still actively preferring matter over antimatter through mechanisms we don't yet understand. The detection of antimatter clouds in our galaxy has opened an entirely new window into cosmic physics, revealing processes that operate on scales far beyond anything we can reproduce in terrestrial laboratories. These invisible clouds represent one of the universe's most closely guarded secrets, announcing their presence only through the brilliant flash of their own annihilation. As we continue to study these phenomena, we inch closer to understanding the fundamental forces that shape our cosmic environment and the mysterious processes that continue to create antimatter billions of years after the Big Bang. The mysteries of quantum gravity have long perplexed physicists, presenting paradoxes that seem to challenge our fundamental understanding of spacetime itself. At the heart of these puzzles lies the enigmatic nature of black holes and their relationship with quantum mechanics. However, a revolutionary concept has emerged from the depths of theoretical physics that might hold the key to resolving these cosmic riddles: gravastars. These exotic objects represent far more than mere alternatives to black holes. They have become crucial testing grounds for our most advanced theories of quantum gravity, offering insights that could reshape our understanding of reality at its most fundamental level. As we embark on this exploration of gravastars within the framework of quantum gravity theories, we enter a realm where the familiar laws of physics dance on the edge of comprehensibility. Gravastars occupy a unique position in the landscape of quantum gravity research, serving as theoretical laboratories where the competing forces of general relativity and quantum mechanics meet in dramatic confrontation. Unlike black holes, which present seemingly insurmountable paradoxes when quantum effects are considered, gravastars offer a framework where these fundamental forces might coexist harmoniously. The significance of gravastars to quantum gravity theorists cannot be overstated. These objects provide a concrete mathematical structure within which to test the predictions of various quantum gravity theories. Where black holes create information paradoxes and infinities that plague our equations, gravastars present finite, well-defined boundaries that quantum field theory can more readily address. Theory suggests that the extreme curvature within what would traditionally be considered a black hole's interior is prevented by quantum effects that create a repulsive force, effectively halting gravitational collapse before a singularity can form. Loop quantum gravity predicts that when matter reaches a critical density, quantum geometric effects become dominant, creating what theorists call the quantum bounce. This bounce transforms the would-be black hole into a gravastar, with the collapsed matter rebounding outward to form the characteristic vacuum energy shell. The mathematics of this process aligns remarkably well with the gravastar model, suggesting that these objects might be the natural outcome of gravitational collapse in a quantum theory of gravity. String theory, another leading candidate for a theory of quantum gravity, also finds gravastars to be objects of profound interest. In string theory's higher dimensional framework, gravastars represent solutions that avoid the problematic singularities that plague black hole models. The theory's prediction of additional spatial dimensions provides new avenues for understanding how the gravastar's internal structure might be supported by quantum effects operating in these extra dimensions. Within string theory, gravastars are often viewed as fuzzballs, extended objects with finite size rather than point-like singularities. This interpretation suggests that what appears to be a vacuum shell in our familiar three-dimensional space might actually be a complex structure extended through the theory's additional dimensions. The mathematics of string theory provides natural mechanisms for creating the exotic matter states required to maintain a gravastar structure, lending theoretical support to their existence. The firewall paradox, one of the most perplexing problems in black hole physics, finds potential resolution in gravastar models. This paradox arises from the apparent contradiction between the equivalent principle, which suggests that an observer falling into a black hole should experience nothing unusual at the event horizon, and the requirements of quantum mechanics, which seem to demand that information cannot be lost. The paradox suggests that a firewall of high-energy particles should exist at the event horizon, creating a barrier that would incinerate any infalling observer. Gravastars elegantly sidestep this paradox by eliminating the event horizon altogether. Without an event horizon, there is no boundary where quantum effects must create a firewall. Instead, the gravastar surface provides a physical boundary where information can be preserved and processed according to the standard rules of quantum mechanics. This resolution has attracted considerable attention from theorists seeking to understand how gravity and quantum mechanics can be reconciled. The holographic principle, which suggests that all the information contained within a volume of space can be encoded on its boundary, finds natural application in gravastar physics. The principle arose from black hole thermodynamics, where it was discovered that a black hole's entropy scales with the area of its event horizon rather than its volume. This scaling suggests that the event horizon somehow encodes all the information that has fallen into the black hole. For gravastars, the holographic principle takes on new meaning. The gravastar surface becomes a true physical boundary where information can be stored and processed. Unlike black holes, where the holographic encoding remains mysterious and paradoxical, gravastars provide a concrete surface where quantum field theory can describe how information is preserved and manipulated. This makes gravastars particularly attractive to theorists working on the holographic description of gravity. The mathematical framework of gravastar physics provides explicit mechanisms for information processing that are absent in black hole models. The quantum field theory on the gravastar surface can describe how information is encoded, stored, and eventually released, providing a complete picture of the object's thermodynamic evolution. This completeness makes gravastars particularly valuable for testing our understanding of quantum gravity. Recent advances in quantum gravity theory have further strengthened the case for gravastars. Developments in the anti-de Sitter conformal field theory correspondence, a powerful tool for studying quantum gravity, have shown that gravastar-like objects naturally emerge from quantum field theory calculations. These results suggest that gravastars are not merely mathematical curiosities but might represent the true fate of matter undergoing gravitational collapse in a quantum theory of gravity. The study of gravastars has also revealed deep connections between quantum gravity and condensed matter physics. The exotic matter states required to maintain a gravastar structure are analogous to quantum condensates studied in laboratory settings. These connections have led to new insights into the nature of spacetime itself, suggesting that the fabric of the universe might have more in common with condensed matter systems than previously imagined. Beyond the familiar tapestry of stars and galaxies that illuminate our night sky lies a vast hidden universe, populated by objects so elusive they challenge our very conception of cosmic reality. These invisible entities drift through the cosmic void, their presence felt only through the subtlest gravitational whispers and the most sensitive instruments of modern astronomy. As we venture deeper into this shadowy realm, we discover that the universe's most profound secrets are often concealed in plain sight, waiting to be unveiled by those bold enough to look beyond the visible spectrum. The cosmos harbors countless mysteries that reveal themselves only to the most persistent observers. While telescopes capture the brilliant light of distant stars and the swirling arms of spiral galaxies, they miss entirely the dark territories where stranger objects dwell. These hidden entities outnumber their luminous counterparts by staggering margins, forming a parallel universe of invisible matter and energy that shapes the very structure of space and time itself. Among the most enigmatic of these hidden entities are the dark galaxies, ghostly structures that contain almost no stars yet possess the gravitational mass of entire galactic systems. These phantom galaxies drift through the cosmic web like invisible leviathans, their presence detectable only through their gravitational influence on nearby luminous matter. Composed almost entirely of dark matter and hydrogen gas, they represent failed attempts at galaxy formation, cosmic nurseries where the spark of star formation never quite ignited. The discovery of dark galaxies has revolutionized our understanding of cosmic evolution. These objects suggest that the universe contains far more structure than previously imagined, with vast networks of dark matter halos supporting invisible galaxies that never developed the stellar populations we associate with normal galactic formation. Some astronomers estimate that dark galaxies may outnumber visible galaxies by factors of 10 or more, creating a hidden cosmic infrastructure that influences the motion and evolution of every luminous object we observe. Within these dark galaxies, hydrogen gas swirls in complex patterns, occasionally betraying their presence through radio emissions detectable by specialized telescopes. The gas moves according to the gravitational dictates of unseen dark matter, creating velocity patterns that map the invisible scaffolding of these ghostly structures. Some dark galaxies show evidence of attempted star formation, with small pockets of gas showing signs of collapse and heating, only to be quenched by mechanisms that remain poorly understood. Wandering through the vast emptiness between galaxies, another class of invisible objects pursues solitary journeys across cosmic distances. These rogue black holes, ejected from their parent galaxies through gravitational interactions or galactic mergers, travel at tremendous speeds through intergalactic space. Their presence is revealed only when they occasionally encounter and consume stray matter, creating brief flashes of X-ray emission that quickly fade back into darkness. The existence of rogue black holes was first suspected when astronomers noticed unexplained gravitational lensing effects in otherwise empty regions of space. These wandering monsters, some containing the mass of millions of suns, bend light from distant galaxies as they pass between us and more distant objects. Their trajectories tell stories of violent galactic encounters, cosmic billiard ball collisions that occurred billions of years ago and continue to influence the distribution of matter throughout the universe. Some rogue black holes travel in pairs, binary systems ejected together from their parent galaxies. These cosmic fugitives spiral around each other as they journey through the intergalactic medium, slowly losing energy through gravitational wave emission. Eventually, they will merge in spectacular collisions that send ripples through space-time itself, events that can be detected by gravitational wave observatories even when the black holes themselves remain invisible. The theoretical zoo of invisible objects extends far beyond dark galaxies and rogue black holes into realms where exotic physics creates entities that challenge our understanding of matter itself. Among these are the hypothetical neutrino stars, objects so dense that even neutrinos, the most weakly interacting particles in the Standard Model, become trapped within their gravitational embrace. These objects would be virtually undetectable through any conventional means, interacting with ordinary matter only through the weakest of forces. Neutrino stars represent a theoretical extreme where the universe's most abundant particles, which normally pass through entire planets without interaction, become concentrated to such densities that they form gravitationally bound objects. The conditions required for neutrino star formation push the boundaries of known physics, requiring densities that exceed even those found in neutron stars. If they exist, these objects would be among the most exotic structures in the universe, composed entirely of particles that barely acknowledge the existence of ordinary matter. Even more exotic are the cue balls, theoretical objects predicted by certain extensions of the Standard Model of particle physics. These are non-topological solitons, stable lumps of scalar field energy that maintain their structure through quantum mechanical effects rather than gravitational binding. Cue balls could range in size from microscopic particles to objects with planetary masses, all held together by the self-interaction of exotic scalar fields. The search for cue balls has driven astronomers to look for unexplained gravitational effects in regions of space where no visible matter exists. These objects will be completely dark, emitting no electromagnetic radiation while still exerting gravitational influence on their surroundings. Some theories suggest that cue balls could be components of dark matter, invisible particles that make up the majority of the universe's mass but interact only through gravity. Axion condensates represent another category of invisible objects that could populate the hidden universe. These theoretical structures arise from the Bose-Einstein condensation of actions, hypothetical particles proposed to solve certain problems in quantum chromodynamics. Axion condensates would form when large numbers of these particles cool to temperatures near absolute zero, creating macroscopic quantum objects with properties unlike anything in ordinary matter. The formation of axion condensates could occur in the early universe or in the cold depths of intergalactic space, where temperatures approach the cosmic microwave background radiation. These objects would be essentially invisible to electromagnetic observation but could be detected through their gravitational effects or their influence on the propagation of electromagnetic radiation through space. Some theoretical models suggest that axion condensates could form cosmic strings or domain walls, extended structures that stretch across vast distances through the universe. These objects would be thinner than atomic nuclei but could extend for millions of light years, creating invisible barriers that influence the motion of galaxies and the distribution of matter on cosmic scales. The study of these invisible objects has profound implications for our understanding of cosmology and fundamental physics. They suggest that the universe contains far more structure and complexity than visible observations reveal, with entire categories of objects existing in a shadow realm beyond the reach of conventional telescopes. The gravitational effects of these invisible entities shape the evolution of visible matter, creating the cosmic web of galaxies and galaxy clusters that we observe today. Recent advances in observational techniques have begun to reveal the signatures of these hidden objects through their subtle influences on the visible universe. Gravitational lensing surveys map the distribution of dark matter, revealing the invisible scaffolding that supports visible galaxies. Gravitational wave detectors capture the collisions of invisible black holes, providing direct evidence of objects that emit no light but create ripples in spacetime itself. The search for invisible objects has also driven the development of new theoretical frameworks that challenge our understanding of the fundamental nature of reality. These theories suggest that visibility and existence are not synonymous, that the universe contains vast realms of matter and energy that interact only weakly with the familiar particles and forces of everyday experience. As we continue to explore this invisible cosmos, we are reminded that our perception of the universe is limited by the narrow window of electromagnetic radiation that our instruments can detect. Deep within the cosmic void, separated by vast expanses of nearly empty space, could there exist entire galaxies composed entirely of antimatter? This possibility, once relegated to the realm of science fiction, has emerged as a serious theoretical consideration among cosmologists grappling with the fundamental asymmetries of our universe. These hypothetical antimatter galaxies would shine with the same brilliant light as their matter counterparts, their anti-stars burning anti-hydrogen and anti-helium in nuclear furnaces that mirror our own sun, yet they would remain invisible to us as antimatter structures, betraying their exotic nature only through the most subtle observational signatures. The theoretical foundation for antimatter galaxies rests on one of the most perplexing mysteries in cosmology, the apparent absence of antimatter in the observable universe. According to our current understanding of particle physics, the Big Bang should have created equal amounts of matter and antimatter, yet today we observe a universe dominated almost entirely by ordinary matter. This asymmetry, known as the baryon asymmetry problem, suggests either that some unknown process destroyed most of the antimatter in the early universe, or that antimatter was somehow segregated into regions beyond our current observational reach. The segregation scenario opens the tantalizing possibility that antimatter galaxies could exist in isolation, separated from matter-dominated regions by vast distances that prevent catastrophic annihilation events. In this model, the early universe underwent a process of matter-antimatter separation, with different regions evolving along divergent paths. While our local cosmic neighborhood became dominated by matter, distant regions might have developed into antimatter-rich territories, complete with antimatter galaxies, antimatter stars, and perhaps even antimatter planets. An antimatter galaxy would appear remarkably similar to a normal galaxy when observed from afar. Antiprotons and positrons would form antihydrogen atoms that emit photons identical to those produced by ordinary hydrogen. Antistars would shine with the same spectrum as normal stars, their surface temperatures determined by the same nuclear physics that governs stellar evolution in our matter-dominated universe. The gravitational forces that shape galactic structure would operate identically on antimatter, creating spiral arms, galactic bars, and central bulges that mirror the morphology of familiar galaxies. However, the boundaries between matter and antimatter regions would be marked by spectacular annihilation events. Where the tenuous gas of intergalactic space meets antimatter counterparts, mutual annihilation would produce intense gamma-ray emission, creating bright annihilation edges that could serve as observational signatures of antimatter galaxies. These boundary regions would glow with characteristic gamma-ray energies of 511 keV, the signature of electron-positron annihilation, along with high-energy gamma rays from proton-antiproton interactions. The search for antimatter galaxies has driven astronomers to examine cosmic ray data with unprecedented precision, looking for the telltale signatures of antihelium nuclei. Cosmic rays, high-energy particles that pervade the galaxy, consist primarily of protons and helium nuclei accelerated to tremendous energies by supernova explosions and other violent astrophysical events. In our matter-dominated galaxy, antihelium nuclei are virtually non-existent, produced only in trace amounts by high-energy particle collisions. The detection of antihelium in cosmic rays would provide compelling evidence for antimatter galaxies. While single antiprotons can be produced through conventional particle interactions, the creation of antihelium nuclei requires conditions that are extremely rare in our matter-dominated universe. The presence of antihelium would suggest that somewhere in the cosmos, antimatter stars are burning antihydrogen and ejecting antihelium through stellar winds and supernova explosions, much as ordinary stars produce and distribute the heavier elements we observe in cosmic rays. Recent experiments aboard the International Space Station have pushed the sensitivity of antihelium detection to unprecedented levels. The Alpha Magnetic Spectrometer, a sophisticated particle detector, has analyzed millions of cosmic ray events, searching for the rare signature of antihelium nuclei. While no definitive detection has been made, the experiments have established upper limits on the abundance of antihelium that constrain the possible existence of nearby antimatter galaxies. The theoretical models for antimatter galaxy formation suggest that these objects would produce their own antimatter clouds through processes analogous to those that create the interstellar medium in ordinary galaxies. Antimatter stars would end their lives in antimatter supernovae, ejecting processed antimatter elements into the surrounding space. These antimatter clouds would serve as the raw material for subsequent generations of antimatter stars, creating a self-sustaining cycle of antimatter stellar evolution. The antimatter clouds surrounding these galaxies would be detectable through their interaction with the cosmic microwave background radiation. Anti-electrons in these clouds would scatter photons from the cosmic microwave background, creating distortions that could be measured by sensitive microwave telescopes. The Sunyaev-Zeldovich effect, normally used to detect hot gas in galaxy clusters, could also reveal the presence of antimatter clouds if they exist in sufficient quantities. Observational constraints on antimatter galaxies come from several independent sources. Gamma-ray telescopes have surveyed the entire sky, searching for the intense gamma-ray emission that would mark the boundaries between matter and antimatter regions. The absence of such signals places strict limits on how close antimatter galaxies could be to our own cosmic neighborhood. Current observations suggest that if antimatter galaxies exist, they must be separated from matter-dominated regions by distances of at least several hundred million light-years. The cosmic microwave background radiation provides another constraint on antimatter galaxies. The remarkable uniformity of this primordial radiation suggests that matter and antimatter were mixed on large scales in the early universe, making it difficult to explain how they could have separated into distinct regions without leaving detectable signatures in the cosmic microwave background. Sophisticated computer simulations of the early universe have shown that the required level of matter-antimatter segregation would likely produce temperature fluctuations in the cosmic microwave background that exceed those actually observed. Despite these constraints, some theoretical models continue to allow for the existence of antimatter galaxies in the distant universe. These models invoke exotic physics from the very early universe, suggesting that quantum fluctuations or phase transitions could have created domains of matter and antimatter that evolved separately. In these scenarios, antimatter galaxies would exist in regions so distant that their annihilation signatures would be redshifted beyond the detection capabilities of current instruments. The search for antimatter galaxies has also motivated the development of new theoretical frameworks for understanding cosmic evolution. Some models propose that antimatter galaxies could exist in parallel bands or extra dimensions, interacting with our universe only through gravity. These scenarios would explain why antimatter galaxies remain invisible to electromagnetic observation while still contributing to the total gravitational mass of the universe. Advanced computer simulations have been developed to predict the observational signatures of antimatter galaxies under various theoretical scenarios. These models account for the complex interactions between matter and antimatter in the intergalactic medium, the propagation of gamma rays through cosmic distances, and the effects of cosmic expansion on annihilation signals. The results provide detailed predictions for what current and future telescopes should observe if antimatter galaxies exist. The implications of discovering antimatter galaxies would be profound for our understanding of fundamental physics and cosmology. Such a discovery would require a complete revision of our models for the early universe, suggesting that processes beyond the standard model of particle physics played a crucial role in cosmic evolution. It would also raise fascinating questions about the possibility of antimatter life and the potential for antimatter civilizations developing in isolation from our matter-dominated region of the universe. Future observational missions may finally resolve the question of antimatter galaxies. Next-generation gamma-ray telescopes with unprecedented sensitivity will search for the faint annihilation signals that would mark the boundaries of antimatter regions. In the vast theater of cosmic phenomena, two of the most enigmatic entities present themselves as mirror reflections of fundamental mysteries that challenge our understanding of reality itself. Gravastars represent hidden structures that masquerade as familiar objects while concealing exotic physics within their deceptive shells. Antimatter galaxies embody missing substances that should exist in abundance yet remain tantalizingly absent from our observable universe. These two phenomena, though seemingly unrelated, share profound connections that illuminate the deepest questions about the nature of space, time, and the hidden mechanisms that govern cosmic evolution. The parallel between gravastars and antimatter extends far beyond their mutual invisibility. Both represent fundamental challenges to our assumptions about the fabric of spacetime and the processes that shape cosmic structure. Where gravastars question the inevitability of singularities and the nature of gravitational collapse, antimatter galaxies challenge our understanding of cosmic symmetry and the mechanisms that led to the matter-dominated universe we observe. The hidden structure of gravastars presents a cosmic sleight of hand, where objects that appear to be black holes actually conceal radically different physics beneath their surfaces. This deception operates on multiple levels, from the macroscopic appearance of the object to the microscopic quantum processes that maintain its structure. Similarly, antimatter galaxies represent a cosmic hide-and-seek game, where entire galactic structures could exist in plain sight, their true nature concealed by the identical electromagnetic signatures they share with ordinary matter galaxies. Both gravastars and antimatter galaxies emerge from the same fundamental tension between theory and observation that drives modern physics. Gravastars arise from the incompatibility between general relativity and quantum mechanics, representing an attempt to resolve the paradoxes that plague our understanding of extreme gravitational environments. Antimatter galaxies emerge from the disconnect between the symmetric laws of particle physics and the asymmetric universe we observe, suggesting that vast regions of space might harbor the missing antimatter that theories predict but observations fail to detect. The theoretical frameworks that support these phenomena share remarkable structural similarities. Both require exotic physics that operates beyond the boundaries of our current observational capabilities. Gravastars demand exotic matter with negative pressure and unusual equation of state properties that have never been directly observed. Antimatter galaxies require segregation mechanisms that operated in the early universe, creating regions of space where antimatter could evolve in isolation from ordinary matter. These requirements push both phenomena into the realm of speculative physics, where theoretical elegance must substitute for empirical verification. The observational challenges posed by gravastars and antimatter galaxies mirror each other in striking ways. Both phenomena would appear nearly identical to conventional objects when viewed through electromagnetic radiation, requiring subtle gravitational or high-energy signatures to reveal their true nature. The detection of gravastars relies on minute differences in gravitational wave signatures, tidal effects, and the behavior of matter in extreme gravitational fields. The identification of antimatter galaxies depends on the detection of annihilation radiation, antihelium in cosmic rays, and the subtle distortions they would create in the cosmic microwave background. The concept of symmetry breaking plays a crucial role in both phenomena. Gravastars represent a breaking of the expected symmetry between gravitational collapse and black hole formation, introducing quantum effects that prevent the formation of classical event horizons. Antimatter galaxies embody the ultimate expression of broken matter-antimatter symmetry, suggesting that the universe's fundamental asymmetry might be more complex than previously imagined, with regions of space evolving along entirely different evolutionary paths. The possibility that gravastars could form in regions dominated by antimatter opens fascinating avenues for theoretical exploration. Antimatter would undergo gravitational collapse in precisely the same manner as ordinary matter, creating conditions where gravastar formation becomes possible. An antimatter gravastar would possess all the exotic properties of its matter counterpart, with an antiparticle vacuum shell preventing the formation of a classical event horizon. These objects would be doubly invisible, concealing both their gravastar nature and their antimatter composition beneath a facade of apparent normalcy. The formation of antimatter gravastars would require the same exotic physics that supports ordinary gravastar formation, but with the added complexity of antimatter evolution in isolated cosmic environments. The quantum field theory that describes vacuum fluctuations and exotic matter states would operate identically in antimatter regions, creating the same conditions necessary for gravastar formation. However, the boundary between matter and antimatter regions would introduce additional complications, as the annihilation of matter and antimatter at these interfaces could influence the formation and stability of gravastars in boundary regions. The observational signatures of antimatter gravastars would be even more subtle than those of their ordinary matter counterparts. The gravitational waves produced by antimatter gravastar formation would be indistinguishable from those produced by ordinary matter systems, as gravity couples identically to matter and antimatter. The detection of such objects would require the identification of both gravastar signatures and antimatter indicators, a double challenge that pushes observational capabilities to their absolute limits. Both phenomena raise profound questions about the nature of information and its preservation in extreme physical environments. Gravastars offer potential solutions to the black hole information paradox by eliminating the event horizon that threatens to destroy information. Antimatter galaxies preserve information in a different way, maintaining the symmetric information content of the universe by segregating rather than destroying antimatter. These different approaches to information preservation suggest that the universe may employ multiple strategies for maintaining the fundamental conservation laws that govern physical processes. The thermodynamic properties of gravastars and antimatter galaxies reveal additional connections between these phenomena. Both systems exist in states of delicate equilibrium, maintained by the balance between competing forces that operate on vastly different scales. Gravastars balance quantum pressure against gravitational collapse, while antimatter galaxies balance annihilation destruction against segregation preservation. These equilibrium states suggest that the universe naturally evolves toward configurations that maximize the preservation of information and structure. The role of vacuum fluctuations connects gravastars and antimatter galaxies through the quantum nature of spacetime itself. The vacuum energy that supports gravastar shells arises from the same quantum field fluctuations that could have driven matter-antimatter segregation in the early universe. These fluctuations represent the fundamental graininess of spacetime at the Planck scale, where the classical concepts of matter and geometry break down and give way to purely quantum descriptions of reality. The mathematical frameworks used to describe gravastars and antimatter galaxies share deep structural similarities rooted in field theory and general relativity. Both phenomena require extensions of standard physics that invoke exotic matter, unusual vacuum states, and non-trivial topology. The equations that govern gravastar dynamics and antimatter evolution emerge from the same underlying principles of quantum field theory in curved spacetime, suggesting that these apparently disparate phenomena may be manifestations of the same deeper physical principles. The experimental and observational programs designed to detect gravastars and antimatter galaxies employ complementary strategies that together probe the full range of cosmic phenomena. Gravitational wave detectors, cosmic ray experiments, gamma-ray telescopes, and precision measurements of stellar dynamics all contribute to the search for these elusive objects. The synergy between these different approaches suggests that the discovery of either phenomenon would likely accelerate progress in detecting the other. The philosophical implications of gravastars and antimatter galaxies extend beyond their immediate physical significance to questions about the nature of scientific knowledge and the limits of observation. Both phenomena force us to consider the possibility that the universe contains vast realms of hidden structure and missing substances that lie beyond our current observational reach. They remind us that the electromagnetic radiation that forms the basis of traditional astronomy provides only a narrow window into cosmic reality, and that the most profound discoveries may await in the invisible territories that lie beyond the reach of conventional telescopes. In the vast catalogue of cosmic objects that populate our universe, few capture the imagination quite like black holes. These gravitational monsters, born from the collapse of massive stars, have become icons of modern astronomy, regions of spacetime where gravity is so strong that nothing, not even light, can escape once it crosses the point of no return known as the event horizon. But what if everything we think we know about black holes is fundamentally wrong? This revolutionary possibility emerged in 2001 when two physicists, Paul Mazur from the University of South Carolina and Emil Mottola from Los Alamos National Laboratory, proposed one of the most radical ideas in modern astrophysics. Their theory suggested that the objects we identify as black holes might actually be something entirely different, exotic structures they called gravastars, short for gravitational vacuum stars. The gravastar hypothesis challenges our most basic assumptions about what happens when matter undergoes gravitational collapse. According to conventional theory, when a star more than about 25 times the mass of our Sun exhausts its nuclear fuel, the outward pressure from fusion reactions can no longer support the star against its own gravity. The star's core collapses catastrophically, crushing matter to infinite density at a point called a singularity, while the surrounding spacetime becomes so warped that it forms an event horizon, a boundary beyond which nothing can return. Mazur and Mottola proposed a radically different scenario. Instead of collapsing all the way to a singularity, they suggested that the star's interior might undergo a phase transition, a fundamental change in the state of matter itself. At the moment when gravitational pressure becomes overwhelming, the fabric of spacetime itself might respond by entering an exotic state known as a de Sitter vacuum. This de Sitter vacuum represents one of the most mysterious concepts in modern physics. Named after the Dutch mathematician Willem de Sitter, it describes a state of spacetime that contains no matter or radiation, yet possesses a strange property: it exerts negative pressure, effectively pushing outward rather than inward. This negative pressure creates a repulsive gravitational effect that could halt the collapse of matter before a singularity forms. The internal structure of a gravastar, as envisioned by Mazur and Mottola, would be unlike anything in our normal experience. At its core would be a sphere of de Sitter vacuum, empty space that paradoxically possesses energy and exerts pressure. This quantum vacuum core would be surrounded by an incredibly thin shell of exotic matter, perhaps only a few Planck lengths thick. This shell would be composed of matter in a state that we have never observed directly, existing at the boundary between normal spacetime and the strange de Sitter interior. From the outside, a gravastar would appear virtually identical to a black hole. It would possess the same mass, the same gravitational field, and the same effect on nearby objects. Spacecraft orbiting a gravastar would follow the same trajectories as those orbiting a black hole. Light passing near a gravastar would be bent by gravity in exactly the same way. Even the powerful gravitational waves produced when two gravastars collide would be nearly indistinguishable from those created by merging black holes. This remarkable similarity makes gravastars nearly perfect imposters. The gravitational field outside any spherically symmetric object depends only on its total mass and distance, regardless of how that mass is distributed internally. This principle, known as Birkhoff's theorem, means that we cannot easily distinguish between a black hole and a gravastar using observations from outside the object. However, the internal differences between black holes and gravastars are profound. While a black hole contains a singularity, a point where the laws of physics break down completely, a gravastar would have no such pathological region. Instead of infinite density concentrated at a point, the gravastar's mass would be distributed in its exotic matter shell, with the interior remaining empty de Sitter space. The absence of a singularity resolves several troubling paradoxes that have plagued black hole physics for decades. In traditional black hole theory, the singularity represents a fundamental breakdown of our understanding of physics. At this point, density becomes infinite, space-time curvature becomes infinite, and the equations of general relativity cease to provide meaningful predictions. The gravastar model eliminates this problem entirely by preventing the formation of a singularity in the first place. Perhaps even more significantly, gravastars would not possess event horizons. The event horizon of a black hole represents a point of no return, a boundary that forever separates the interior from the external universe. Once something crosses the event horizon, it can never communicate with the outside world again. This leads to profound questions about the nature of information and causality in our universe. The absence of an event horizon in gravastars eliminates several paradoxes that have puzzled physicists for generations. One of the most famous is the black hole information paradox, which arises from the conflict between general relativity and quantum mechanics. According to quantum mechanics, information cannot be destroyed, it can only be transformed or hidden. But if matter falls into a black hole and disappears forever behind the event horizon, what happens to the information it carried? Stephen Hawking's discovery that black holes can evaporate through quantum radiation only deepened this paradox. If a black hole eventually evaporates completely, carrying away the information that fell into it, this would violate one of the fundamental principles of quantum mechanics. The information paradox has led to decades of theoretical work and continues to challenge our understanding of the relationship between gravity and quantum mechanics. Gravastars offer an elegant solution to this dilemma. Without an event horizon, information falling toward a gravastar would never be permanently lost. Instead, it would be stored in the exotic matter shell, potentially recoverable through future observations or interactions. This preservation of information would maintain the consistency of quantum mechanics while still explaining the gravitational effects we observe. The quantum vacuum at the heart of a gravastar represents another departure from conventional black hole physics. Instead of the empty nothingness that classical physics would predict, quantum field theory tells us that even empty space is filled with virtual particles, pairs of particles and antiparticles that spontaneously appear and disappear on timescales too short to observe directly. In the extreme conditions near a black hole, these virtual particles can be separated, with one falling into the black hole while the other escapes as Hawking radiation. In a gravastar, the de Sitter vacuum core would be in a fundamentally different state. Rather than the quantum vacuum we observe in normal space, it would exist in a configuration with negative pressure, a state that could theoretically persist indefinitely without the gradual evaporation that affects black holes. This stability would allow gravastars to exist for timescales far longer than the current age of the universe, potentially outlasting even the protons that make up ordinary matter. The formation mechanism for gravastars remains one of the most challenging aspects of the theory. Unlike black holes, which form through the relatively straightforward process of gravitational collapse, gravastars would require the creation of exotic matter and the establishment of a de Sitter vacuum core. The exact physical processes that could accomplish this transformation remain speculative, involving aspects of quantum gravity and exotic matter physics that we don't yet fully understand. Some theoretical work has suggested that gravastars might form during the final stages of stellar collapse when quantum effects become important. As matter approaches the point where a singularity would form, quantum corrections to general relativity might become significant enough to prevent further collapse. The resulting phase transition could create the exotic matter shell and de Sitter core that characterize a gravastar. The search for observational evidence of gravastars has become one of the most intriguing challenges in modern astronomy. Since gravastars would appear nearly identical to black holes from the outside, distinguishing between them requires extremely subtle observations. Some researchers have proposed looking for slight differences in gravitational wave signatures, variations in the behavior of matter spiraling into these objects, or other minute deviations from black hole predictions. Recent advances in gravitational wave astronomy have opened new possibilities for testing the gravastar hypothesis. The collision of two gravastars would produce gravitational waves with characteristics that might differ slightly from those of merging black holes. As our detectors become more sensitive and our theoretical understanding improves, we may finally be able to determine whether the cosmic objects we call black holes are truly the gravitational monsters we imagine, or whether they are something far stranger, bubbles of exotic spacetime masquerading as the universe's most extreme objects. From the outside, a gravastar appears to be an exact twin of a black hole. The spacetime around both objects bends and warps in precisely the same way, creating what scientists call identical external metrics. To any distant observer, their gravitational fields look indistinguishable, the same crushing pull that bends light and time itself. The same fierce gravitational embrace that captures passing matter and accelerates it to incredible speeds, heating it until it glows with the fury of 1,000 suns. But hidden within this cosmic masquerade lies a profound mystery. While black holes and gravastars may look identical from afar, they harbor fundamentally different secrets in their cores. The question that keeps astrophysicists awake at night is simple yet profound: how can we tell them apart? How do we distinguish between nature's most extreme objects when they wear identical masks? The challenge is immense. A gravastar's surface sits precisely where a black hole's event horizon would be, the critical radius where escape velocity equals the speed of light. Yet despite this perfect camouflage, the universe may still whisper their secrets to those who know how to listen. The answer lies in the most subtle signals nature produces: gravitational waves. When two massive objects spiral toward each other in their final cosmic dance, they send ripples through spacetime itself. These waves carry the very fingerprints of their source, encoded in frequencies and amplitudes that tell the story of their violent origins. The gravitational waves from gravastars are remarkably similar to those of black holes, but the tones and fadings are different. Like two master violinists playing the same complex piece, a trained ear can detect the subtle differences in timbre and resonance. Scientists have discovered that gravastars should produce slightly different gravitational wave patterns, variations so minute they exist at the very edge of our current detection capabilities. The difference lies in what happens during the final moments of collision. When two black holes merge, they create a characteristic pattern, an initial in-spiral as the objects circle each other, followed by a brief but intense merger phase, and finally a ring-down as the newly formed black hole settles into its final state. This ring-down phase carries the signature of the event horizon, that invisible boundary where information disappears forever. Gravastars, however, possess actual surfaces. During collision, these surfaces can vibrate and oscillate in ways that event horizons cannot. The result should be additional gravitational wave signatures, subtle echoes that reverberate through spacetime like sound bouncing off the walls of a vast cathedral. These echoes would arrive milliseconds after the main signal, carrying information about the structure and composition of the colliding objects. The Laser Interferometer Gravitational Wave Observatory, or LIGO, has been listening to these cosmic symphonies since 2015. Each detection tells a story of cataclysmic collisions billions of years ago, events so violent they briefly outshine entire galaxies in gravitational wave energy. But hidden within these signals could be evidence of something far more exotic than black holes. When LIGO detects a gravitational wave event, teams of scientists pore over the data with microscopic attention to detail. They search for anomalies, for patterns that don't quite match the theoretical predictions for black hole mergers. In the case of gravastars, they hunt for what they call echo signals, those subtle reverberations that might occur if the colliding objects have surfaces rather than event horizons. The search is painstaking and requires extraordinary precision. The gravitational waves that reach Earth are incredibly weak. They stretch and compress space by distances smaller than 1,000th of a proton's width. Detecting echoes within these signals is like trying to hear a whisper in a hurricane, requiring signal processing techniques that push the boundaries of modern technology. So far, the echoes remain elusive. The dozens of gravitational wave events detected by LIGO and its European counterpart Virgo are all consistent with black hole mergers. Yet they cannot definitively rule out gravastars. The cosmic truth remains tantalizingly out of reach, hidden in the noise and uncertainty that plagued the most sensitive measurements ever attempted. Perhaps the most direct way to distinguish between these cosmic twins lies not in the waves they produce, but in the light they bend. The Event Horizon Telescope has given us our first glimpse of what we believe to be a black hole's shadow. The iconic image of M87, the dark silhouette against the glowing accretion disk surrounding it. This groundbreaking photograph shows us the very edge of the point of no return, where light itself cannot escape. The image reveals a ring of fire surrounding a dark void, exactly as Einstein's equations predicted more than a century ago. The shadow we see is not the black hole itself, but rather the absence of light from the region within the event horizon. It represents the ultimate boundary of the observable universe, the place where physics as we understand it breaks down completely. But what if that shadow belongs to something else entirely? What if M87 is actually a gravastar masquerading as a black hole? Current telescope technology cannot distinguish between a black hole and a gravastar based on their shadows alone. The Event Horizon Telescope, despite its remarkable achievement, operates at the very limits of what is physically possible. Creating a more detailed image would require a telescope the size of Earth's orbit, a feat that remains firmly in the realm of science fiction. We stand at the threshold of a new era in astronomy, where the tools we've built to study the universe are revealing mysteries that challenge our fundamental understanding of reality. The question of whether gravastars exist may ultimately be answered not by looking at individual objects, but by studying the statistical properties of many gravitational wave events over decades of observation. If gravastars are common, patterns should emerge in the data, subtle signatures that reveal the presence of these exotic alternatives to black holes.